So a scientific law, as opposed to like a traffic law or some law in the penal code, a scientific law is a summary of observed behavior, which means that it's measurable, right? Whether it's quantitative or qualitative, you can measure it. Remember, a theory is attempting to explain why this law is the way it is. A theory is a hypothesis assembled in an attempt to explain why the what happened. The scientific law is the what happened. So a law summarizes what happens. A theory or a model is an attempt to explain why it happens. A few of the major laws that we see in science, one of the many conservation laws in science, the law of conservation of mass, right? One of the things that you guys should have already been exposed to is the fact that mass cannot be created or destroyed. It can simply change forms. It is true once we get into some high-level stuff that it can actually change forms into energy, using the equation E equals mc squared, but that's a little bit over our heads at this point. We also have the law of conservation of energy, which is also known as the first law of thermodynamics. Thermodynamics, the changing of heat energy, right? Meaning energy cannot be created nor destroyed. It can only change forms. Now that should have been introduced to you back in the 2nd grade or 3rd grade sometimes back then. But this is a law. Now in terms of why this is the case, right, we're not talking about. We're just saying that this always is the case. It's a scientific law. Now, scientists observe these laws and then they create theories or models in attempts to explain these laws, but they are human. They make mistakes frequently. For example, data misinterpretation, right? Sometimes there's a phrase that says the numbers never lie, the numbers don't lie, which is true, the numbers don't lie. However, we don't always know what they're trying to say, right? Misinterpreting the data. Emotional attachments to theories, sometimes people just want something to be the case, and they kind of rearrange or force the data to show that. When they have, it leads to a loss of objectivity. When you think that something can't possibly be the case or something can't possibly not be the case, you're losing your objectivity and you're going to begin to fail to make those observations that are so important to science. Politics, right? This is a really bad one. I guarantee you've heard some sort of response to climate change data, and you've heard some sort of political argument against it. That really has no place in science. However, because humans are involved in politics, unfortunately will spill over into science, and it shouldn't. However, it does. Ego. People want to show that they were right, that their idea was correct, right? Because they have some sort of attachment to it, some sort of selfish attachment to it. One of the things that happens a lot today, profit motives. The problem with vaccines these days, all the mistrust with vaccines, really stems, for the most part, to one individual. And this individual, published work that provided data that suggested that vaccines were very, very closely related to autism. And in fact, he faked that data. That was not real data. It was non-reproducible. No one was able to recreate that data. And one of the things that's easy to see is that person became absolutely filthy rich because of that fake data and all the attention that went along with it. Now, there are some other ramifications. That person is not enjoying the fruits of those lies right now. That person's in jail, but this person made millions and millions and millions and millions of dollars on that whole idea. Fads, right? Some things become popular, and so scientists will ignore certain things and pay attention to other things based on fads. Wars, unfortunately, one of the greatest pushers of scientific development is war. Right? One of the reasons that the atomic bomb was created is because of war, but the science that went into understanding the atom that allowed for the atomic bomb to be created probably wouldn't have been done for another 20 or 30 years if it hadn't been for the motivation of war. Also, religious beliefs, right? Scientists do have religious beliefs. There's a popular fad that all scientists are atheists, and that's simply not true. Also, you probably heard in school that there have been various religious beliefs that have held back scientists. For example, Galileo, right? He was forced to recant his astronomical observations in the face of strong religious resistance. Right? They were simply observations, right? They were observations. They weren't opinions. They were definitely the type of thing where, like, hey, if you look through this telescope, I should say, like, you will see these things. And the religious powers of the day said that no, that's a deception, and he was forced to recant. And to say in the face of strong religious resistance is really pretty an understatement. And it turns out that these astronomical observations were surprisingly accurate. Galileo was laying it down back in the day. Lavoisier, Anton Lavoisier, the father of modern chemistry, one of the first guys to demand quantitative analysis, was beheaded due to political affiliations in the French Revolution. For the simple reason that he was associated with tax collectors. He was a tax collector for a very short time himself, but his family, his aristocratic family, had close ties to tax collectors going back, and so he was executed as "quote unquote" an enemy of the state, even though he was doing science research. He was doing chemistry. It was pretty unfortunate because he was executed via the guillotine at a fairly young age before he had been able to complete his work. That being said, he had massive contributions to the field of science that could have been greater if it weren't for these political affiliations. He happened to be on the losing side of that French Revolution. So one of the ideas that really came out of war was the need for better explosive. For example, our understanding of the three states of matter actually was pushed forward by our need for better weapons. So like nuclear devices, and also the fact that fertilizers can help plant growth through the utilization of nitrogen. Again, these things came from major wars. And so, explosives, right? Explosives don't just involve combustion explosions. It involves any movement from the solid or the liquid state into the gas state. Why? Because there is a massive and very rapid expansion when you move from the liquid or the solid state to the gas state. You're talking about expansion of volume on the scale of about 2,000 times. And so the force behind that is going to be very destructive. In fact, one of the most damaging bombs ever dropped was in recent years, called the Moab, the mother of all bombs. It was actually a concussive bomb. It was not a big fireball. And what it was designed to do is to collapse caves. But that sort of research was motivated by warfare. But this simple idea, when you have things that are in the solid state, and the liquid state, and the gas state, they behave differently, right? This is all based on the kinetic molecular theory, okay, the KMT, the idea that all molecules are in movement, right, constant movement. Now, the extent of that movement, the type of that movement is going to vary. And so when we see the solid state here, we see things very, very tightly packed together. Typically, this is the most dense version of some substance. They are locked together. They're not allowed to move around one another. However, they do vibrate. Right? There's quite a bit of vibration. And so there are different types of vibrational motion. We can have bending, right? We can have one atom in the matrix move up and down, just typical bending. We can have stretching, right? We can have the bond length between any of these two atoms change and go back as a result of vibration. We can also have asymmetrical stretching, maybe just this side, push towards this side, away from this side, again, changing the bond lengths. This is simple vibrational motion because these things are locked in place. They're not allowed to move. When you have something move into the liquid state, you can see that there's a slight bit of expansion here. Not a significant amount, but there is typically, in most substances, there's a slight bit of expansion here. Now, the type of motion is going to change. There is also still going to be some vibrational motion, don't get me wrong, but we have the addition of what's known as rotational motion and something that's written over here, but it's also present in the liquid state, translational movement, right? Translational motion. Now, we can see that we can have rotation in the y-axis, we can have rotation in the z-axis, but what can happen is this little molecule right here, it can slide past these other molecules, and as long as it stays, in close contact, close proximity to the other liquid molecules, it'll remain liquid. But the fact is that this molecule can translocate, which is where we get this term translational motion. It can change its location. Which is why liquid is one of the states that is considered to be a fluid, because it can flow past itself. But when we transition from the liquid state to the gas state, not only do we have this vibrational motion, not only do we have this rotational motion, we still have translational motion, but we have the addition of independent motion, where these gas particles are most certainly moving past one another. They're changing locations. They're translocational. But they're also wildly independent of one another. When this liquid molecule right here was trying to move, when it was trying to translocate, it had to stay in close proximity to these other molecules. And so it had to move relative to the other liquid molecules in that sample. With this gas here, it does not matter, especially in a ideal gas. It does not matter where these other molecules are. Each of these molecules are independent of one another, especially if we remember the definition of what it means to be an ideal gas.